Hello everybody, today I'm going to discuss the solution to a USACO problem, a problem that was given at the Platinum Division in December 2017. And the problem is named Greedy Gift Takers. For those of you who are not used to what Olympiad problems are, they basically are problems where, unlike let's say Code Forces or other online judges, you need to find a bunch of observations to solve the problem and you can get partial credit. So these are things I'm going to explain as I solve the problem, and I will go through every step of the solution in order to be able to understand the ideas that help us solve the problem. So in this problem, we are given n cows, and we know that these cows lie in a queue. And basically, at each step, we know that the queue that is at the front of the queue, the cow that is at the front of the queue will receive a gift. And basically, we want to find out how many cows will never receive a queue. This is what the problem is asking us to do. And we know that the process is going to be indefinitely long because the farmer has an infinite supply of gifts. So now the first idea that comes to our minds is of course to simulate the process. So just do it using any naive algorithm that just takes the cow at the front of the queue and just moves it back to the queue. We know that unlike an usual queue, each cow will cut a bunch of cows in the queue. So this cow with one will cut one cow at the back of the queue. So it won't be last, but second to last. And we know this information for each other cow. Now, basically, we want to simulate the process fast enough, but the issue is that the number of steps until we get to a position where they will just keep moving around can be very big. And this is not really helping us in any way. So we need to find some observations related to what these cows are. So let's analyze the input they are given. And I'm going to transform these values into n minus their initial values. So basically just working with the positions. And let's see what happens now. So from 1 to 3, we go to 2, 1, 3. Then we go to 2, 1, 3, and again to 2, 1, 3. And we can see that this will keep happening. Now, this process stopped because we had a queue that would always spawn at the front of the queue. We have a cow that will always spawn at the front of the queue. So basically it would be easy to say that if we have a cow that will always spawn at the front of the queue, then the process will stop. But we need to find also other important things that help us. This is helpful, but not enough. Another thing that we observe is that we know that this cow was never at the front of the queue. So basically, something we can deduce from here is that if a cow is never at the front of the queue, no other cow that's behind this cow at the beginning would ever be at the front of the queue. Because if this was never reached, none of these would be reached either. And from here, we can also deduce that the set of the cows that are going to be the first ones will always form a prefix. And what this means is that we can even think at something like a binary search later on the road. Because if we know that we have a set of cows that works, a smaller set can also work. But we need to still find some other observations. So far, we found, let's say, 2 key observations. First off, if we have a CI that after transformation is 1, then we would be done. And also, answer is a prefix. So the set of cows that works is a prefix, which can help us find a binary search later on the road. Now, we need to find more observations based on this path, because in terms of the binary search, we will still need to implement some function that help us deduce whether we can do it or not. Now, if we don't have something that's equal to 1, Let's analyze another case. So let's analyze something where we have two 2's and a 3. So the cows would go like this: 1, 2, 3, 2, 1, 3, 1, 2, 3, and so on. So if we don't have a 1, then two values equal to 2 would be enough, because of the same reason. So we can now safely deduce that if we have 1, 1 or 2 2's or 3 3's, it will be fine, and so on. But at the same time, also having something like 2 2 3 or 2 3 2 or something would guarantee us that we have at most 3, because they will just keep moving and none of the cows at the back will ever be touched. So basically we can expand this property, or this one from here, into something like at least I cows with C of I smaller or equal than I. And so at least I with C of I smaller or equal than I, because what will happen is that they will form a cycle. And now that we found this observation, we can deduce the fact that we can just check using binary search if this property ever occurs for a given I. Because if this happens, then the prefix we chose is never going to be an answer, so we need to choose a smaller prefix. Now, how do we get here? Because of course this observation is important, but you might think at easier ways to get this done. Now, from my experience of solving the problem, I tried a bunch of greedies and a bunch of implementations that relied on maybe things like sets or stacks or other related things. But a lot of the shortcomings I had were based on the fact that we could also have an input where we have a bunch of big numbers, and then all of a sudden 2's, or even something like 3's here. So let's say that we even have something like this. So we have a 10, then a 3, then a 2, then another 10, then a 2. Now, this is problematic because we wouldn't have a cycle that completely integrates every cow, but a cycle that contains a subset of the cows. And while the idea explained below covers this case, some of the greedies out there don't do that. And it's very easy to do mistakes relying on things like that. So in order to recap, we can binary search on the answer, and if there is no I such that we have at least I that are smaller than the given value, then we can use that answer as the prefix, and then we can move to bigger prefixes. Now, this will work, it will be good enough, and it's actually very close to what the intended solution is. There is also another approach that relies more on just simulating the brute force fast. We can start with knowing that we need 1 cow, 2 cows, 3 cows, and so on for each of the values out there. And we can interpret also this as a range query problem. So let's say that we have a C of I equal to 4. We can just say that on the range from 4 to n, depending on implementation, we either add or subtract 1. In my other solution, I added 1 because I was starting with negative values. And we can now turn this into a rather typical lazy segment tree problem, where we want to find the first position such that we will have a maximum query which will return us at least 0, because this means that we touched this condition. This is also a method worth trying and worth knowing, and I'm also going to explain both of these solution codes. So basically, the first approach that relies on binary search, I just binary search the answer, and then at each step of the binary search I check if there is an I such that the prefix sum of the frequencies of the first x positions is at least equal to I. If this happens, then this is not a valid answer, otherwise it is. Take note that in both of these solutions I will print in the end n minus answer minus 1, because I'm finding the number of cows that are going to be the first ones. Now with the segment tree solution, I just plugged in the lazy segment tree solution, and the lazy symmetry class I have, and I just made it use maximum queries. And I did the range update for a certain suffix and then just a query where I want to check if the maximum is at least 0. Take note that I'm building the segment tree with a negative I for each position. Again, the same approach, but it's slightly slower because the binary search has a better constant. Now, basically, in order to solve this problem, we have to rely on a bunch of observations that are deduced from analyzing the input, but also we need to think of the right way to solve it, be it data structures or binary search. Both of these ways introduce us rather short solutions that don't take too much time to implement. Now, if you enjoyed watching this video, please like the video, subscribe to the channel, and also press the bell button for more notifications. Also, if you want me to cover more problems, be it Olympiad problems or problems from other competitions, please comment in the video so that I know what to cover. In addition, if you want to work more closely with me, please check out my website in the description or ways to contact me so that we can help you reach your goals, be it in Olympiads, USACO, or in general to become better at algorithms and problem solving. So until the next time, please make sure to watch my videos, and also good luck in your contest. Thank you. Cheers.